All right, good afternoon, everyone. Sorry I'm a little later than usual. There is the link to Poll Everywhere where we have our daily quiz for today. Date, because I forgot to do that. All right, so we're missing Josh. Got it. All right, well, I've got 2 o'clock, and it is everyone there. Can you please respond to me? Thumbs up, unmute yourself, say hello, whatever, just so I know. Well, I got 8 thumbs up, 2 thumbs up, 3. All right. Well, go to that daily quiz. You'll now see your question. The question for today is, you share it for Zoom. What is the dimension of the vector space R5? What is the dimension of the vector space R5? So, my coffee's currently brewing right now. I'll give you until it's done, or at least 1 more minute. Whichever one is longer. So you got a second, answer that question. What is the dimension of the vector space R5? And coffee is done. I'm gonna give y'all, I think we got everyone in, maybe missing one. Missing one response. Get it in. I'll give you just 15 seconds. If you're having issue getting into Poll Everywhere, then just send it to me as a private chat, your response. Who's missing it? All right, locking answers in 5, 3, 2, 1. Locking answers now. Okay, cool. We got it in at the last minute. So, question for today is, what is the dimension of R5? And the answer is 5. That was one of the theorems that we had at the end of class on Tuesday. So let me get my whiteboard up. So we said the dimension of any Euclidean space, dimension of Rn, for n being any number, well, this is always equal to n. Okay. If you wanted to confirm, you'd be able to create a basis. And a nice, very simple basis for any Euclidean space is just having vectors. So number of vectors meaning equaling the number of entries you have for each row. So a good basis for R5 would be vectors 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, and last but not least, 0, 0, 0, 0, 1. Those 5 vectors would form a basis. Relatively easy to see that these are linearly independent, because if I try to see what gives me information for the first row, I'll only be able to use this first vector. Second row will only come from the second vector. Any information will be in the third, and so on. Okay. So answer here, I guess just to write it out, the dimension of R5 would be 5. Questions, concerns, comments, emotional outbursts, anything?
I have a question.
Yeah, go for it, Josh.
So when is it n-1?
Not n-1. We had the space dimension of all polynomials of degree n or less. So that an x to the n plus an minus 1 x to the n minus 1. Let's see if I can get it all here. I kind of fit it in. But all your polynomials of degree n or less, that wasn't n minus 1. It was n plus 1. I'm trying to think. I don't know I don't know of vector space off the top of my head. That would be always n minus 1. So this might be what you were thinking of.
Yeah, it was that. Just mixed it up.
Cool. Any other questions? I'm listening while I'm go mute my phone because apparently it's going crazy. And it's not near me. All right, I'm not hearing anything else from y'all. So we're gonna keep moving on. Okay, so I asked y'all to look at section 6.1 or watch the video that I posted of, I can't remember his name off the top of my head, but the guy's small lectures on eigenvectors and eigenspaces. So that's what we're going to be talking about all day today, at least all day Tuesday, maybe next Friday, depending on how quickly we get through. Okay? And I'll also try to save, as long as I don't just get in a zone and keep talking, I'll try to save the last 5 minutes of class today for homework if you all got questions on that. Just putting it out there. But if you want to see some kind of solutions I was at least looking for, you are more than welcome. I posted them to last week's learning module underneath the homework assignment. So, eigenvectors, eigenspaces, eigenvalues. We do eigenvalues here instead of spaces, are what we're going to be studying. And these eigenvectors and eigenvalues are things that are going to keep randomly popping up in your studies after linear algebra. These are some extremely important values, the eigenvalues, and extremely important vectors. And what we're probably going to end this semester on is something called diagonalizable matrices, and then see why that is very important for application process. Because as we started off the semester, we're always, there's a lot of different things, whether you do it with differential equations, whether you do it statistics, you're trying to do least square solutions, etc. You're always going to end up with a system of equations. Always end up with a system of equations, and the goal is to solve it. Now, eigenvectors, eigenspaces, diagonalizable matrices, it's just another way to solve for that solution without having to find the inverse. Because as we started off the class, we said, okay, well, the easiest thing would be to multiply by an inverse. And we had this tool at least to find out whether or not it existed, but either case, it was a lot of effort to just calculate what the inverse of that A matrix is. And as we get through some of this theory with eigenvectors and eigenvalues, we get into some diagonalizable matrices, or called diagonalizable matrices. We're going to see where eigenvectors and eigenvalues end up simplifying the process for us. Okay? So the goal is then just say, okay, what are these things? What are eigenvectors and eigenvalues? And eigenvectors and eigenvalues are vectors and values that solve a particular equation for a matrix A. So, definition. Let A be an n by n matrix. So we're assuming this is a square matrix. Got to be a square matrix. N is just some general number, so it could be a 3 by 3 matrix, 4 by 4, 10 by 10, 1 million times 1 million. Don't really care, just as long as it's a square matrix. Okay. So a scalar lambda. So a scalar lambda. Lambda is the Greek letter. This is the lowercase lambda. If you're familiar with Greek life, it's a little bit, you'll probably see this lambda used a lot. That's capital lambda. In mathematics, we use lowercase lambda. So that value lambda is said to be an eigenvalue of a matrix A. If there exists a non-zero vector X such that A times that vector is equal to lambda times that vector. So what we're describing there is essentially is just saying that multiplication by this matrix A for this particular vector is essentially the same as multiplying that vector by a scalar. So if we can find an eigenvalue in such a vector, or a value for lambda in such a vector, we call it an eigenvalue. And we also say that the vector X is the eigenvector corresponding to lambda. Oh gosh, that's corresponding down there. Corresponding to lambda. So it's a nice definition, and in this we get two pieces. We get what are eigenvalues, and it's these scalars. And then associated with eigenvalues are eigenvectors. So really when we're trying to pose this question of finding eigenvalues in eigenvectors, we're really solving for two things at the same time. We know what A is, we'll always know what A is, and we have to come up with these scalars, these eigenvalues, and these eigenvectors that are going to satisfy this equation. That A times that vector is going to give me lambda times that vector. So that's just the definition. So I'm going to leave it there for a second. Give me a thumbs up if you have it written down, please, so I know that I can move to a new slide. Thank you, Nabari. 3, 4, maybe I'll just 5-ish more seconds. All right, so let's play around with that equation. So I'm going to just write it up here in the top right so we remember. What we're looking for is values of lambdas in vectors such that that equation will hold. A times that vector is going to be equal to lambda times that vector. I'm just trying to get a little bit more familiar with this equation, eigenvalues and eigenvectors. Let's just start off with a nice simple example where I'm going to give you an eigenvalue and we want to just kind of confirm. So let A just be the 2 by 2 matrix, or -2, 1, 1. The question I want us to answer is lambda being 3 an eigenvalue for this matrix A. So is lambda equals 3 an eigenvalue for this matrix A? So I know the first step in trying to answer this question is I need to be able to plug that in. I need to be able to look at this equation, A times X equal to lambda times X. And I'm going to replace that lambda with a 3. So AX equals 3 times X. Okay. And then my goal is after that to say, okay, can I find a vector that's going to make this work? Can we find an X Oops, rewrite that. So we want to be able to find an X that makes this true. Now, we're used to solving systems AX equals B. Right, where again, this A is just some matrix. I don't care what it is most of the time, just some matrix. This X is representing my unknowns. And this B is a vector of knowns. So if I have it set up like that, we have the tools to solve it, but that's not what we currently have right here. This A times X equals just 3 times X. But can I manipulate this equation at all to kind of recreate this a matrix times my vector that is an unknown equals to some other vector that I do know? Well, the key is to just subtract 3x from both sides. This leaves me with A times that vector x minus 3 times the vector x. Well, that's equal to my 0 vector. Now, what do both of those two terms on the left-hand side of this equality, what do they have in common?
The X vector.
Yeah, that X vector. And I have to be careful in how I do it, but what can I factor out from both of those terms?
The X vector.
Yeah, I get to have you on repeat, right? Yeah, it's just the X vector. So I can factor out that X vector, and I have to be careful in what I write here. That it's going to be equal to 0. Now, just to recall or remind y'all, if I had, let's say, go back to our algebra days, x squared plus 1, and I wanted to factor out an x, I'd be left with x plus what? Or sorry, wow, x squared plus 1. I wanted x squared plus x. That's not going to help us. X squared plus 1 is not going to help us at all. If I have x squared plus x, and I wanted to factor out an x, I'd be left with x plus what? Yeah, thank you, Ellen, for putting in chat. It would be a 1. Right? And then the real numbers in our algebra, our 1 is our multiplicative inverse. Okay? Because when I distribute this x back through, I want particularly x times 1, x times my identity element, to get me back to x. Now, what was my identity element for any matrix, for any vector space? Sorry, not for any vector space, for matrices. What was my identity element for matrices? It had a particular name for it.
You could repeat the question?
What is the identity element for matrices?
Is it 1?
Not 1, but what was the matrix that acted like 1 for us?
I.
What was that, Nabari?
I.
Yeah, that I, our identity matrix. Remember that identity matrix is just a matrix with ones all along the diagonal and zeros elsewhere. It's a nice little shorthand way to write it. We had ones all along the diagonal and zeros elsewhere because when we multiplied this matrix by any other matrix, it always just returned that other matrix. It acted like my one. It is my identity element. Okay. So it seems like maybe that I is just kind of randomly appearing, but it's appearing because that's my identity element for matrices. So that when I distribute back through this x vector, when I look at 3 times the identity times the x vector, well, 3 times the identity times the x vector, well, identity times anything gives me that anything. But now, after I factor out that x, I now actually have a matrix times a vector of unknowns equal to a vector of knowns. Because we know what the zero vectors look like in any Euclidean space or a matrix space. Right? It's just a matrix with all zeros. So now I have this set up to where I can actually solve this thing. Right? I have ways to solve it. And I want to say, okay, can then I find a solution for this new equation? Can I find a solution for a minus 3i times x equal to 0? We're going to do that, but questions yet? Any questions? All right, I'm going to assume that everyone's paying attention and just following along. So let's rewrite some of our information. We're trying to solve a minus 3i times x equal to 0. And our A matrix was 4, -2, 1, 1. So first things first, I need to figure out what A minus 3i looks like. Well, this is 4, -2, 1, 1, minus 3 times my identity matrix. I'm working with 2 by 2 matrices, so I can assume that my identity matrix is a 2 by 2 matrix, which means, again, ones all along the diagonal and zeros elsewhere. So this is going to be just taking it step by step. If you shortcut it and you kind of get to the final answer, that's fine. Multiply that 3 through. It'll be 3, 0, 0, 3, leaving me with 4 minus 3, which is 1, 0, or -2 minus 0, which is -2, 1 minus 0, which is 1, and 1 minus 3, which is -2. So that is what that matrix A minus 3i now looks like. 1, -2, 1, -2. That means when I go to solve this system, let's see if I can fit it all right here on this one slide so I don't have to go to anything else. What I'm trying to solve is 1, -2, 1, -2 times some x vector, some x of unknowns. x1, x2. It's got to be equal to my 0 vector, which is 0, zeros. And from there, we would just say, okay, throw this into an augmented matrix and row reduce. 1, -2, 1, -2, augmented with 0, 0. And I can see there's one easy row reduction to do here. What would be the row reduction? I want to modify row 2. I'd take row 2 and do ones.
I have a question.
What's up?
Since your matrix is a 2 by 2, why is your x unknown matrix vector not a 2 by 2?
So remember, go back to where we started. X, well, it's because it's just supposed to be a, maybe I didn't say it in here, but these eigenvectors are an Rn. Good question. I'm glad I can clarify that. So it's actually supposed to be an actual vector, a vector in Euclidean space. So for whatever size these are, A is a matrix, X is a column vector. So that's why I'm writing it when I go back to here. When I'm doing it in general, that's why I wrote them as column vectors.
All right, got it.
Good question. Thank you. Any other questions real quick? All right, so then what's that row operation? Because I want to reduce this matrix down to as close to the identity matrix as I can. Get into my reduced row echelon form. So what should I do? Row 2 is equal to row 2.
Minus
What?
row 1.
Minus row 1.
Yeah, minus row 1. Minus row 1. And this will leave me with 1, negative 2, whoops, 0, 0, 0, 0. And by how we set this up, that first column corresponds with coefficients for x1. Second one corresponds with coefficients for the variable x2. So this gives me that I now have the system of equations. X1 minus 2x2 has got to be equal to 0. And x2 is what type of variable?
Free variable.
Yeah, free variable, right? Because we get that row of zeros. Okay. So I'll give you all a second to write that down because I do have to go to a new board. I'll try to rewrite some of our summary information and keep the last solution all in one page. Okay. So give you all 5 more seconds. 1. So we're trying to solve a minus 3I times x equal to 0. We found then that x1 minus 2x2, where my vector x is just the general entry, some general unknown vector with entries x1 and x2, where they satisfy that equations, which means then that x1 is double whatever x2 is going to be, and I can choose x2 to be anything I want. So in general, a vector that would satisfy this equation that I was looking for, okay, any vector would just look something like 2 whatever is in the second spot times some number that's in the second. Just a variable. X2 again can be anything that I want, but if I pull out that constant, that free variable, I actually see what I need to use. A vector that would satisfy this equation is really just some number times the vector 2, 1. So there's actually many solutions to this. It's the first observation. So for the system that we were trying to show, we were trying to show that 3 is an eigenvalue. So we took that, what is it, 4, negative 2, 1, 1, multiplied it by my x vector for this equation that we were trying to solve. I can write it up here again in blue. I'm going to kind of see it in the condensed form. But for that equation, any vector of the form any vector of the form, some constant, I'm just going to go back to C for constant, 2, 1 is a solution.
Professor, I have a question.
What's up?
So since x2 is a free variable, I could have picked anything, and then I would have did my vector, my x vector. So if I picked my x2 to be 1, my x1 would be 2, and that's how you have this one right here. But if I had picked 4, then my x1 would be 8, and that would be my x vector as well.
Yeah, absolutely. The line of reasoning I was using there for that equality, though, is saying, you know, x2 is technically just some constant, right? We're filling it in, but it's a constant. And it's a constant that is being multiplied in both the first row and second row. So I could undo my scalar multiplication there. And that's why you see me pulling out that x2. And then that's where we get to see that really it's just whatever that value, kind of like what you're saying, right? Whatever the value is I choose, I just need to multiply it by the vector 2, 1, and that's going to give me a solution to the system. So there's two different ways of approaching it, but yeah. All right, and that's why instead of writing x2 here again, I just wrote any general constant. So now we get to answer the overall question. I'm about to sneeze. Excuse me.
Bless you.
Thank you. So let's go back, recap real quick. Our goal is to figure out if lambda being 3 is an eigenvalue for A, which means that I needed to be able to find some vectors x that solved this equation. A times whatever that vector is has got to be equal to 3 times that vector. Did we do that?
Yeah.
Yeah, we did. So we know that 3 is an eigenvector, or eigenvalue, sorry, is an eigenvalue. Oops, there's supposed to be an E there. For that matrix, 4, -2, 1, 1. Whoops. Oh, it's not going to let me write in that bottom right-hand corner because there's a button there on my Zoom screen that I can't move, I don't think. So I'm missing putting that 1 in the bottom right of the matrix. It's just because I'm having issues actually writing it in with my little crappy stylus. But that means 3 is an eigenvalue for the matrix 4, -2, 1, 1. Because for that value, I can find solutions to that equation. A times x is equal to 3 times x. We also not only found in the process that 3 is an eigenvalue, we also found out what its eigenvectors look like. Okay? So we're going to test just a couple solutions here just to see that it can be a lot of different solutions. There can be a lot of different eigenvectors for a single eigenvalue. But any questions so far?
The eigenvector would be the C to 1.
Yeah, so let's write it out actually. So any eigenvector, whoops. For the eigenvalue, lambda being 3, is of the form some constant times 2, 1, where C is a real number. Now stated slightly differently, but also using some notation. Any eigenvector for my eigenvalue lambda 3 is in the span of that vector 2, 1. So these are two equivalent ways of writing it. So let me try to put some, nah, let's not use yellow. These are just two different ways of writing what our eigenvectors look like. Right? Both equivalent, but as we can kind of see, one's a little bit shorter than the other. Part of the reason why we love notation. All right, well, I said we're going to test these values. So I'm going to go back and give me a thumbs up if you got this written down. Cool, I see most people now. All right, so let's just confirm some. Right? The theory says it should work, but first time we see it, we might want to make sure that it actually did. Maybe we made a mistake the first time. Or, it's just like whenever you're doing your algebra, right? You find your solutions for your polynomial. The best way to make sure they didn't make a mistake is to plug them back in and see if it is true. So I want someone to pick a vector in that span of 2, 1 for me.
2, 1.
2, 1, sure. So consider the vector 2, 1. Then I should have that 4, -2, 1, 1 times 2, 1 is equal to 3 times 2, 1. And just an interesting way to write, like for a reader, I'm testing to see, I'm not sure at this point in time if these are equal. I want to test to see if they are. I can just put a little question mark over the equality sign. It's just one way I like to write whether or not, is this statement true without having to write a lot of stuff out. So let's do the multiplication on both sides. I'm going to go ahead and do the right-hand side because scalar multiplication is a little bit easier than matrix multiplication. 3 times 2 is 6. 3 times 1 is 3. I'm still wondering if these two things are equal. And now I got to figure out, what is that multiplication on the left-hand side going to be? Well, remember with matrix multiplication, it has been a little while since we've done it. It's row by columns. So I'm going to have a 4 times a 2 plus a -2 times 1, taking the first row, multiplying it by the first column. That finishes that row's multiplication by every column. So I move on to the next row, which would be a 1 times a 2 plus a 1 times a 1. Well, 4 times 2 is 8. I'll be subtracting a 2, and then I'll have a 2 plus a 1. And then I can see from there that yes, those two are equal because 8 minus 2 is 6 and 2 plus 1 is 3. Okay? But I told you that that's a span. Any vector in this span will satisfy it. So let's just do one more calculation real quick. Someone give me another vector that would be in the span of 2, 1. Someone other than Eliam, since he got the first one.
8, 4.
8, 4. So then I need to do this multiplication. 4, -2, 1, 1. Times 2, 1 equal to 3, or 8, 4. Sorry, I don't know why I wrote 2, 1 again. 8, 4 is equal to 3 times 8, 4. And again, I'm unsure if this is true right now, so I just like to write that nice little question mark over that equality. Do that right-hand side because it's a little bit easier. What 3 times 8 is 24. And 3 times 4 is 12. do the matrix multiplication on that left-hand side. This will be 4 times 8 plus -2 times 4, and then 1 times 8 plus 1 times 4. Again, I'm unsure at this point in time if these things are equal, so I just put a nice little question mark over that equality. But then 4 times 8 is 32. And I'll be subtracting 8 in the numerator, or in the, not the numerator, in the bottom entry, I'll have an 8 plus a 4. And I see that through that arithmetic, that simple arithmetic in there, that yeah, these are going to be equal to each other. Okay, questions? All right. So just from looking at this example, we get one interesting thing, is that once we identify what an eigenvalue is, which we don't have the tools yet to do it, we're going to set up how to solve them. That's what we're going to work on Tuesday. But once I have an eigenvalue, there's more than one eigenvector, and I also figure out what generates those eigenvectors. And since I have a vector that can generate all other vectors, that actually turns out to be a basis. And then from that basis, I can create a vector space. So this creates another definition for us, and something called the eigenspace. You rewrite that P. So the eigenspace of a matrix A corresponding to a particular lambda. And we're going to just always reserve lambda. If we see it, it means eigenvalue. Lambda means eigenvalue. It is the set of all eigenvalues or eigenvectors. I don't know why I'm messing up eigenvalues and eigenvectors. It's a set of all eigenvectors of A corresponding to lambda. Together with the zero vector. That is what an eigenspace of A corresponding to lambda is. Set of all eigenvectors corresponding to lambda, and then we just throw in the zero vector as well. Now you might ask why we throw in that zero vector. Well, in that definition, we said it's eigenvectors come from solving this equation. And in the definition for eigenvectors, we said that they needed to be non-zero. So technically, eigenvectors can't be the zero vector, and the reason why we make that definition is because it's not interesting. If I set the vectors equal to 0, there's going to be an infinite number of eigenvalues for that eigenvector 0. So it doesn't create a nice, easily studied case, and that's why we made this condition of non-zero. So then we're talking about an eigenspace, and we say it's a set of all eigenvectors, and then we just add on the zero vector at the end. It's because the set of eigenvectors should include 0 to begin with, but to make it a space, i.e. a vector space, we need a zero vector. So always going to be the span of whatever your eigenvector is, the basis for your eigenvector, plus 0. And just kind of explaining why we have to add in that last statement. Okay, but from eigenspaces, eigenvectors, we're going to make a couple observations, and we kind of see it through. And if you recap and go through the process, your notes, you're going to see where these 5 statements come up. Actually 4, because I skipped over reminding all of null space. But this is what's going to motivate us for Tuesday and how to actually find the eigenvalues. So let A be a square matrix, so an n by n matrix, and let lambda be a scalar. Then the following are equivalent. The following are going to be equivalent. So first up, lambda is an eigenvalue of A. Second, that if lambda is an eigenvalue of A, then A minus lambda times the identity matrix times that vector X will give me the 0 vector. Right, we saw that. Third, A minus lambda I is singular. If it was non-singular, that means there'd be only one solution, because then that matrix A minus lambda I would be invertible. As we saw, there's not just one solution. There's not just one eigenvector corresponding to an eigenvalue. There's many. So that if we have a solution or have an eigenvalue, that means in this matrix it's got to be singular. Well then, last but not least.
Wait. So
What's up?
singular in this case means it has more than one solution?
These are all equivalent, yeah. That means you'd have more than one eigenvector. If this matrix right here is singular. And right above it, that was the other term we can use to describe it, an equivalent term, non-invertible. And then if we calculate, last thing, if we calculate the determinant of a singular matrix, what does that determinant have to be equal to? Anyone remember?
0.
Yeah. It's got to be equal to 0. So we didn't actually do this calculation, that last one, but that last part of this theorem is what's going to allow us to find eigenvalues. If I look at the determinant of this matrix, A minus lambda times the identity, I'm going to get what's called the characteristic equation. And then the values of lambda that make that characteristic equation 0, i.e. make the determinant 0, are going to be eigenvalues of my matrix.
Can you say that again? Sorry.
So, where did I start? So I know just determinant gives you what's called the characteristic equation, but you have to be able to find what values of lambda make your determinant of A minus lambda I 0. And then once you have those values of lambda, that means you have your eigenvalues. And so that last one is what we focus on. It's what generates what we call the characteristic equation. We're going to go back and kind of pull some of our algebra back. We're going to remember really quickly how to solve zeros of polynomials, because that's how we find eigenvalues. Dang, well, I didn't leave really the last 5 minutes for homework, but any questions on eigenvalues, eigenvectors, stuff like this?
No.
Give me a thumbs up if you're still here.
No question.
What's up, Eliam?
I said no questions.
Oh, no question. Sorry, I heard I got a question.
No, you probably used to me asking.
Gotcha. All right. So I didn't get up on Blackboard until like 5 minutes before we came to class. Part of the reason why I was running a little late. If you want to start the homework, make sure you watch the videos for next week. He goes through characteristic equation. Also finding your eigenvectors. But we'll go a little bit more in our lecture into finding the basis for your eigenspace. But as you can see right here in this problem, we found what the basis for my eigenspace is for lambda being 3. Well, it's just that vector 2, 1, because any multiple of 2, 1 would give me another eigenvector. So we're going to go through just finding examples of finding eigenvalues, finding their corresponding eigenvectors, and then once we have that, finding our eigenspaces, and i.e. finding the basis for our eigenspaces.
The homework.
Sorry, I know I keep interrupting, Eliam. What's up?
No, I was just gonna ask if the homework for the eigenspaces and eigenvectors is up. Like the web work.
Oh, I gotta still assign it to y'all. It will be here in like a minute.
Oh, I thought that's what you were saying. I thought you were saying you can go ahead and start the homework.
Well, you can now. You refresh, if you have web work up, if you refresh the page, you should see it now.
Okay.
Yep, but you want to watch that, at least watch the video that I posted to Blackboard for next week. So there, it's titled Characteristic Equation. That's what's going to help you find your eigenvalues. So I'd watch that before you attempt, at least. And I also wrote underneath the video, I reposted the video that you were supposed to watch before today on eigenvalues and eigenvectors in that same folder. But you don't need to watch it if you've already watched it. Just wanted to make sure it was there. So all the material is combined together. All right, so we're over. It's 2:52. If you got questions about anything, you're more than welcome to stick around. I'm going to stop the recording right now.